Evening, everyone. We're going to start Chapter 7 today. I believe Chapter 7 has got 4 sections. 7, 1, 2, 3, 4. Today we're going to do 7.1 and 7.2. Essentially, we're going to be looking at how do you estimate the mean of a population when sigma is known. That's the title, so let's put it into English. Imagine that you have collected a sample of 200 people and the mean of that sample is 35, and that's how old they were. So you got a random sample of 200 people and their average age, their mean age in the sample was 35. Up to this point, that's about it, isn't it? We could probably calculate the standard deviation to give you an idea of how varied the numbers were. But we want more than that. So what we're going to learn today is how to estimate what the population is. So can we imagine that the population is adult? Well, actually everybody, right? Everybody in America is the population. So these 200 consist of little babies and 97-year-old grandpas, right? Everybody and anybody could be in that. And that's where this came from. And wouldn't it be nice if we could find a way to put a kind of error band on it so that we can say, this interval of values is where we believe the population mean is. That's essentially what this is going to be about. Now you can do it by hand and then you can do it by calculator. So I'm going to show you how to do it by hand first, and then I'm going to sell you on the fact that the calculator does a much better job. So we're going to look at a thing called the confidence interval. That's what we're going to call these intervals that we're creating. They're going to be called confidence intervals. What we're going to do is we're going to take a percentage and we're going to say the classic normal confidence intervals is a 90%, a 95%, or a 99%. They're the 3 typical percentages that you'll see in everyday statistics analysis. And when I create, say, a 90% confidence interval, what I'm saying is that I'm 90% confident that this particular interval will have the mean of the population in it. Now, I know from my sample, and that 35 hopefully is really close to the mean, but would you also agree it'd be a miracle if it was exactly the value of the population mean? It's going to be a bit out because, you know, every sample's different, right? Some are a little bit bigger, some are a little bit smaller. And that's why we kind of need a little interval. Well, how do you get the confidence interval? It's made up of this formula. It's the mean plus or minus a guy called E. And I'll put it over here. E is called the margin of error. And so the formula becomes X bar plus or minus ZC sigma over the square root of n. So the margin of error is this fella. Well, let's suppose in this story that I'm talking about, somehow or other, we know that the standard deviation is 10, right? Let's just say we know that, because that's when it says here, when sigma is known. Okay, so this guy, this margin of error, right, that's made up of this fella, it's going to be made up of this funny little guy, which I haven't talked about yet, times 10 divided by the square root of the sample size. So who is this funny little guy called ZC? Well, he's a special magic number. When you want a 90% confidence interval, he's called Z 0.9. And he is 1.645 in that situation. If you want a 95% confidence interval, that magic number, that ZC, is called this fella. And he is always going to be equal to, in that situation, 1.96. And then you might want a 0.99. And if you do, you're going to get 2.58. And those guys never change. So if you want to do a 90% confidence interval, you're going to use that number here, right? If you want to do a 99, you're going to use that number here. You see, this depends on the story, but this changes depending on the confidence interval, right? Let's do a 90%, right? Let's suppose the question was, find a 90% confidence interval for the average age of all Americans. Well, in this case here then, that would become 1.645. So I'll just get my calculator and do that. It's a pretty straightforward calculation. 1.645 times sigma, which is 10, divided by the square root of 200. And now I'm looking at a margin of error. I'm going to have to round it off. So let's round it off to 2 decimal places. So it's going to be 35 plus or minus the margin of error, 1.16. And if you take that number away from 35, you get 33.84. And if you add that number to 35, you get 36.16. So what we've just done here is created a 90% confidence interval for what we believe the mean of the population is going to be. So if you could go out there and ask every American their age and find out what the average was, the mean was, we're saying it's in that interval. Or at least we're 90% confident it's in that interval. You can see it's not 100%, right? So essentially, isn't there a 10% chance we screwed up and we just got a bad sample? Right, and the average isn't in this range, right? The average for the population is not in this range. Maybe it's 37, maybe it's 32, right? Something like that. You can't be 100% sure. Well, not really realistically. But here's 100% confidence interval. Would you agree that the average age of Americans is somewhere between everybody's a baby to everybody's 1,000 years old? Would you agree that the real answer is somewhere in that range? And I'm 100% confident that it's in that range. So, can you see it's also a pointless piece of information? Tells you nothing. So you have to restrict yourself to being only a certain percentage confident. A 90% confidence gives me this interval. If I did a 95% confidence, what would change? Well, see this calculation here? The only thing that would change is that I'd use 1.96 instead of that guy. And if I did a 1.96 instead of that guy, I would get 1.96 times 10 divided by the square root of 200. And the answer I'm going to get now is 1.39. So this guy here would become 35 plus or minus, not this number anymore, but 1.39. Well, that would give me 35, take away that is 33.61, and add it on is 36.39. Do you notice that this interval is a little bit bigger than that one? I mean, this one starts at 33.8, and this one starts a little bit further to the left at 33.6, and doesn't the other one start way over here, so the interval is bigger? Why do you think that happened? Because everything else pretty much remained the same. But why is, if you want to be 95% confident, why would you expect the interval just to be bigger? Common sense might tell you.
Maybe to account for margin of error.
Well, the margin of error is what we call this, guys. So I guess we are accounting for that. But if we make it bigger, isn't there more chance we're going to get the right answer in it? So in this interval, there's a 10% chance I'll miss it, right? If you make the interval a little bit bigger to these numbers, can you see that I'm now only going to have a 5% chance of missing it? And I don't have time or patience, but I could do a 99% as well. See if I did the 99%, wouldn't it go even further apart? So that's a truism. A bigger confidence interval, right? A bigger percentage confidence interval will generate a bigger interval and will also generate a bigger margin of error. So if you want to be really sure, shouldn't you make your interval dead big, right? Big range of values. If you're willing to survive a little bit, then that's fine as well. Now I'm going to have to do this because some of the homework questions are it, but it bugs the heck out of me. This textbook has decided that 80% confidence intervals exist. 80% confidence intervals don't exist, at least don't exist in the statistics world, but does exist in this textbook. And if you have to do an 80%, the magic number for this is 1.28. It bugs the heck out of me that they even do that, but I can't take these questions out because there's, you don't get enough practice. Now, did you notice that there's a fair amount of work that we have to do here to get a 90 or a 95% confidence interval, right? Fair amount of work. Especially this bit, right? We have to do this. And that just gives us this little guy here, right, called the margin of error. And then don't you have to add it and take it away? And, the more calculations you've got, isn't there more opportunity to make a mistake? So I am going to show you how that entire process, this one here, right, and then maybe this one here, can be done with the calculator. So if you give me a few moments just to set this up, hopefully, you'll be able to join me. Right, are we all looking at a nice calculator? If you've got yours handy, you might want to talk this through or watch this, kind of do the button pressing. There's my calculator on. Hit the stats button first. Then once you hit the stats button, scroll over to a thing called tests. You see that guy? Guy called tests. So far, so good. Now, the guy that we want is called a Z interval. I think it gets its name because we use that ZC in the calculation, right? Basically the magic number. Now, when I hit this, we're going to be looking, at least in this calculator, at a kind of menu like this, right? It's a little bit more complicated than your typical menus. At the top here, do you see it's flashing data? We'll look at that in a different question. But the one we want right now is the one that's called stats. Now, when I hit that, it's going to ask us to basically fill in the missing details. Well, so I'm scrolling down. In this question, sigma was 10. In this question, the mean was 35. That's the sample mean was 35. In this question, there were 200 people in the sample size. Now, do you see it's called C level, 0.95? That's going to create a 95% confidence interval. Right now, I think the first one I did was a 90, so I'm going to change that to 0.90. And then I'll go down to calculate. And when I hit enter, do you see that 33.84 and the 36.16? That's what I rounded off. Do you see the same interval has appeared? And for, I don't know, for added information, don't they just tell me what the mean and the sample size is anyway? But I knew that, so you're not telling me anything I don't know. Now, suppose I wanted to increase the confidence interval to the new one, called the 95. Then you go Start, move over to Tests, choice number 7, interval. And pretty much I can keep all of this the same and just change this to 95. You see, that's the only thing that needed to alter. Everything else was the same. Then I go down to calculate, and when I hit the enter, do you see my 33.61 and my 36.39, the rounded off guys? Me personally, I would say that the calculated way of doing it is cleaner and less likely to make a mistake, right? Because all you're basically doing is typing in the information that's in the question, right? You're told the X bar, you're told the sigma, you're told the N, you're told what kind of confidence interval you're going to create. You put the package together and you're good to go. You feel comfortable about that? Right. I'm going to put in the 91 just to see it for, for the set. So I'm going to go over to tests. I know it's number 7, so if I hit 7, it saves me scrolling. And I'm going to go to here and put 0.99. That's really all I need to do. And the window for 95%, the interval, for 99% I should say, has grown. It's now 33.18 roughly, and the other guy's about 36.82. Right, let's go back and kind of see a summary of those 3 versions. There's a 90% confidence interval using this information. There is a 95 using this. There is a messy 99 using this. Can you imagine I could do an 80%, a 74%, any weird number that the textbook just feels like they want to do. And I think one of the questions is a 75% confidence interval. I remember seeing that somewhere, and it absolutely made me cringe, but it's a homework question, so we'll do it. These are the standard 3 that you will see in any kind of statistical analysis. 90, 95, and 99. They're the kind of the bread and butter numbers. They kind of make sense. Would you agree that you don't want to do an 80% confidence interval? Because doesn't that mean 20% of the time you're wrong? So if you did 5 of those and you used it to make a decision, your boss isn't going to like you, because isn't one of those 5 times the thing goes belly up and your boss comes back and says, but you said it was in this range, and you go, oops. Well, I don't think that's a good oops, right? And I don't want the government making very important decisions based on an 80% or, God forbid, a 70% confidence interval. Don't you want an interval that at least you feel comfortable? It depends on what you're doing, which one of these 3 is being used. Do you know if it's not that vital and you just want a kind of run-of-the-mill one, 90% is pretty good. So if you were talking about, I don't know, how many people can tell the difference between Pepsi and Diet Pepsi or something, I don't mind a 90%. Right, what's going to happen if I get it wrong? Nothing, right? Nobody cares. On the other hand, if I'm doing some kind of drug trial, wouldn't I probably want one of the higher numbers to make sure that whatever I predict the typical average benefit to that drug, I'm 99% sure it's in this range. So, what's the word I'm looking for? Circumstances decide which of these 3 it's going to be. If you were the person in charge of the trial, the experiment, whatever it is, then you would decide on that. But you got to remember who your readership's going to be. So if it's something really dangerous and very important, and you go for the 90, a lot of people, when they do the peer review, are going to say, I really don't think 90 was a good choice. I really think we want to be sure here, so why don't we be as sure as we can be and do a 99? And you could go back and, fix it and then send in your thing for peer review again. Are we cool? Right. Now, there's a number of questions like this. I'm going to just make up one more, and then we're going to look at a different kind of situation where you still know sigma, but a kind of a different flavor of that same question. So let's see. Oh, the mean number in my sample here is 55. And with this sample size, it's just 5 people. And the sigma is 15. So I'll need a little story for this. A professor is too lazy to find out what the average in his final exam is. So imagine the exam was out of 100. And so rather than spend a lot of time, maybe he's got 200 students, right? He's got tons and tons of them. Rather than do that, he's decided he randomly picked 5 of them, and that's where that came from. And he wants to just get a rough idea, right, what the average for the whole population is. In this world, the whole population is quite small. It's these 200 students, right? So if he wasn't a lazy guy, couldn't he really do it anywhere? He should have. So let's see what this is going to look like. Oh, you tell me, 95, 99, 90, what do you want? What confidence interval do you want? Yeah, I'll have to hear it. I can't read lips. Well, I can, but sometimes I can't read lips. So give me a number, Lauren. It's like you're trying to say something.
95.
Okay. Do you know the hardest questions to ask a student are, give me a guess, give me a number. They think it's a trick question, like you could get it wrong, right? I mean, you've only 3 major ones to choose from. You can't get it wrong, right? So we are going to get a 95% confidence interval. Now, again, I'm going to do it both ways. And then after I've shown you this guy, we're then just going to use calculator if we do any, right, of this type. So let's see. It's the mean, plus or minus the margin of error. It's the mean, plus or minus the magic z-score for 0.95 times sigma over root n. Well, I know this thing is 55. Who has got a good memory? Because I only showed you it once and it's gone now. What's the magic number for a 95%? Who uses?
1.96.
Is that just you got a good memory or you wrote it down and it's in front of you?
I wrote it down.
That's okay. That would be sensible. So 15 over the square root of 5. So that's going to be 55, give or take. Time for the calculator here. I guess I could do it this way. You can see it, right? Clear this out the way. So 1.96 times 15 divided by the square root of 5 looks like 13. Ooh, not good. Let's call it 13.1. If you take 13.1 away from this, you get 41.9. And on the other side, if you add it, you get 68.1. So there is your 95% confidence interval. Somewhere between, well, 42 and 68, very roughly. Somewhere between 42 and 68. That's the average that his entire class of 200 statistics students got. Why do you think that interval is so huge? I mean, from the 40s to almost the 70s. Why is it massively big? What's the main reason for that happening?
Sample size.
Yeah. That is atrociously bad sample size, right? 5. Couldn't you get 5 really good scores by bad luck, 5 really poor scores, 5 all over the place scores? Isn't there a lot of opportunity to just get a bad sample of 5? Now, if you had a sample of 50, isn't it much harder to get an average that's way, way out? And so as that sample size increases, do you notice that it's going to be that number there that changes? And if that number there gets bigger, doesn't this calculation get smaller? And so what you have is big sample size gets you small margins of error. Does that make sense? Big sample size, small margin of error. Here's a question that you're sometimes asked. Let's suppose that I haven't conducted my survey yet, right? I haven't picked the 5 students I want, or the 50 students, or whatever number it's going to be. And so I haven't got this. But I would like to know how many students I need to ask to get a particular margin of error. So imagine the question is, how big does your sample size have to be to get a margin of error equal to, say, 5? So he wants to know how many students he should pick so that when he does this guy here, it's going to be 55, give or take 5, right? Or whatever the answer happens to be. Now, there is a formula for doing that. N, the sample size that you need in this situation, is equal to ZC sigma divided by E all squared. Now you remember ZC is the magic Z score depending on what confidence interval you want. So this question needs a confidence interval. A 95% confidence interval. How big does N need to be to get a margin of error of 5? So that's the full question. So that now means that the sample size N is 95, which is 1.96, times 15 over a margin of error E, which I forgot to put that in, 5, all squared. So I'm going to get the calculator to do that. It's a good idea to put a bracket first. Actually, it's a good idea to put 2 brackets. Although in this case, I think I can get away with 1. Let's just be sure. 1.96 times 15 divided by 5, close brackets, squared. Yeah, that'll be fine. Whoa. You need a sample size of 35 because you can't get 34.6 people, right? So in this question, you don't round off to the nearest whole number, you round up to the next whole number. And you might say, well, why do I need to do that? Remember, you want to get a margin of error of 5 or a little bit less, right? You'll live with a little bit less, but you don't want more. If this number was 34.1, rounding it to 34 might give me a little bit bigger margin of error than I was looking for. So to be safe, basically, round down. And it's always going to be a whole number, right? The number in your sample has to be a whole number. So imagine questions like 31.7, 38.1, and 40.1234, right? If it was 31.7, wouldn't you say you better have 32 people in your sample? If it was 38.1, how many people should you make sure you've got in your sample? Yeah, I see mouse moving 39. And wouldn't you also agree in this last one, wouldn't you still round up to 41 people? So what we have here is a really cool calculation. Won't that tell you how big your sample needs to be to get whatever the margin of error you're willing to live with? So not only can we calculate confidence intervals, can't we, as a different question, calculate what sample size you would need to have a particular margin of error on that? Any questions, or are we good so far? Thumbs up is good. Anybody else? Looking good? Right. So I'm going to see, and I may have forgotten, because I know what I'm like, and I did. I'm going to show you in a few moments what the homework questions for that particular question is. I'm looking at it right now. There's 10 of them, but I'm going to have to close some things off so I can share a screen. And here we go. Are you looking at hopefully 7.1, estimating the mean sigma non? Great. Okay. There's going to be a story attached to these, and that's fine. Let's just tell you kind of the details of what's going on here. So I might, in a few seconds from now, take you through that process, but here it goes. Alan, never knew this bird, but Alan's hummingbird has been studied by zoologists, and suppose a small group of 15 Alan hummingbirds. So in that story, do you see they've told me N is 15? Right, so you're going to have to read a story and suck out from it the numbers you want. Now, the average weight of these birds, so X bar is 3.15 grams. Those things are tiny. You know how much 3 grams is? It's tiny, right? Now, we can assume that sigma in this case is 0.2. That's cool. Now it says find an 80% confidence interval, right? So that's going to be question A. Find an 80% confidence interval. And now I'm going to leave for a moment and go into our camera. Right there. I think my calculator, can you see my calculator? I've got a big screen, so I can get away with it. Right, I'm going to take that information that's here, and I'm going to let the calculator get an 80% confidence interval. So quiz time. What button do I press to get there? Okay, see your lips moving, so stats gets the job. Where do I go now?
Tests.
Okay, so I'm over to tests. Which number is the interval thing that I'm going to use?
7.
7.
Right. Have you noticed it's kind of do the same all the time? Now I'm going to move over to the stats menu and hit enter. Okay, so we are ready to type that in. It should just be a matter of, okay, sigma is 0.2. That's done. The mean in this question is 3.15. That's done. Sample size is 15. That is done. And the confidence level is at a 9.80, right? Because that's what the guy wanted. And then go down to calculate and hit enter. Now, the numbers that we have here are 3.03, 0.08, my eyesight, try it again, 3.0838, and the big side is 3.2162. That's going to be called, I think they called it something like lower, and they called this guy the upper. Can you see where you're going to get the numbers for lower and upper then, right? And the way you would probably write it Yeah, that's how I would write it, right? As an interval. And that's how they're getting you to do it as homework. I don't think it's a big deal. You agree? Good. So let's go back and see what the rest of the questions look like. I have two here. I think it's this one. It is, okay. So in my particular question, I would be writing down 3.0838. And then on the upper limit, I would be writing 3.2162. And then we hit a problem. The calculator doesn't directly tell you the margin of error, right? When you do the calculator thing here, right? Doesn't tell you the margin of error, but we have to know how to get it, right? So there is a way of doing it. So let me go back out. Can I show you? You know the mean, and you know the lower, and you know the upper, right? If I take this number and I compare it against this number, and you take one away from the other, isn't that one of the margins of errors? Isn't that the minus version? So the margin of error can be found by, I can do it with the upper. You could take the upper number and you could take away the mean. So upper, take away the mean. So let's see what that gets me. So that gets me 3.2162, take away 3.15, and that comes out to be 0.0662. Right, visually think about this. Right in the middle is going to be 3.15. On this side, you're going to get 3.0838. And on this side, you're going to get the 3.2162. Isn't that the X bar value? Don't you add the margin of error to get here, and you take away the margin of error to get there? So see if I subtract these two, won't that be the margin of error? Does that make sense? Why this calculation tells you what the margin of error is, right? It's the middle, plus or minus, to get to the two outsides. I know the middle and I know the outside, so that's what the difference is. So there is your margin of error, 0.0662. Are we okay with that? I don't see such happy faces. I don't think we are. Okay, I'm going to pretend and do a couple of those, just that bit of the puzzle, right? And show you how I would find the margin of error in each case. And maybe when you've seen it 2 or 3 times, that's what he's doing, okay. So, suppose I did a totally different question, but I know that the mean is 40, and I know that the interval goes from 32 to 48. How would I get the margin of error? Well, couldn't I take 48 and take away the mean? Now, if you want to think about it, isn't 40 give or take 8 going to get you that guy? Okay. Suppose another one. Suppose the mean was 1.23 and the margin of error was 1.73 and, oh God, I shouldn't have picked that number, but too late now, 0.73. Won't the margin of error be that guy, take away that guy? I'm making the numbers easy to do. Won't the margin of error be 0.5? And if you think about it, if you add 0.5 and take away 0.5, do you see you get that interval? Am I seeing happier faces now? Right? Agreed? Do you need another one, or two gets you the gist of how that's going to work? Do you feel comfortable now? The biggest number in the interval, take away the mean. That's how you can find a margin of error. Here's a different question, totally different question. Suppose that was a, I don't know, 95% confidence interval. And they didn't tell me X bar, the mean of the sample. How could I get it from here?
You could
Yeah, Lauren?
subtract the largest number from the smallest number and divide by 2.
That sounds a pretty good idea. Do you all agree? So, big guy, take away big little guy. What does that come out to be? Well, if you take that guy and that guy and you divide by 2, you get 7.6 divided by 2, and you get 3.8. Does that look right? You want to change your mind? Actually, do you know what you've just found there? You've just found the margin of error. You were close, one little change. I want to find essentially the guy right in the middle, right? That's where X bar is going to live, right in the middle of these two numbers. Does that make sense? Okay, well, Lauren?
Sorry, I thought we were trying to find the margin of error.
In which case, that is exactly what you should have done. So let me ask you the next question, since you're the one that answered that one, you should finish. How would we calculate X bar now?
You would add them and divide by 2.
Have you noticed that the two calculations are very similar, but they generate totally different results? So if you know an interval and you add them together and half it, that's going to get you X bar. If you subtract them and divide it by 2, isn't that going to give you the margin of error? So do you see within that interval, don't you pretty much have everything you could possibly want, as long as you know how to suck it out of the interval? Now, if I know it starts here and it finishes here, can't I figure out where the mean at the middle is, because that's X bar? And can I also find the margin of error? Okay, so let's zoom back out and in and all that fun stuff. Okay, so the margin of error here is 0.0662, right? That's what Mike picks up. Now, here's something we haven't talked about yet. And it's talking about what conditions are necessary for you to do these calculations. Doesn't sigma need to be known? Anything else? No, I put the key in just so you could see it. It has to have a normal distribution of weights. What I'm saying here is that for these questions, we have to assume that the population that it came from is at least approximately normal. And if we can do that, we can get away with it. Technically speaking, but I argue with this book quite a lot, although you don't need n to be large, isn't it just a good idea to make it large if you want to be accurate? So it's not strictly, and that's, I guess, why they're not putting it in, it's not strictly necessary, but it is kind of helpful if you do it. Now, oh well, the answer's there, but we'll come to do that. Interpret your results. If you have an 80% confidence interval, all you're really saying is we are 80% confident that the true average weight of Allen's hummingbirds was fill that in. You notice how I've said a 95% confident, a 90% confident, hate it, an 80% confident, right? Whatever it happens to be. We say it in that way. And it's a bit lawyer-esque. You don't say the probability that we got it right is 80%. We just say that you're 80% confident. do you know that the real answer is either in the interval or it's not? And if it's in the interval, it's 100% right. And if it's not, it's 100% wrong. So if you're talking about probabilities and you're being a bit like a lawyer, that interval here has a probability on, darn it, I'm pointing at things that aren't there again. The interval that my finger was pointing at, this interval here, isn't the population answer in it, in which case the probability that I got it right 1, or it's not in it, in which case the probability I got it is 0. 80% confidence interval just means I'm 80% confident that this interval, somewhere inside it, I've got the answer. So you might think I'm being a little bit like I don't know, a lawyer, but that's how we do these things. Are we cool? Right. Now, as you go through the questions, they come up with one more. So I've got the question in front of me, so I'm just going to tell you what it is. Suppose that we wanted the margin of error to be 0.13. And it's an 80% confidence interval. So has anybody got the magic Z score that you're going to need in your calculation for an 80%?
1.28.
Well done. Right. Now, the size of your sample should be that guy times sigma all over the margin of error squared. So it's going to be 1.28 times 0.2 divided by that fella, all squared. So here goes, put a bracket around it, 1.28 times 0.2 divided by 0.13, close brackets, square the darn thing, and the answer is 3.877. So what do we call that? Because you have to have a whole number. And that is the answer that they were wanting. Technically speaking, I would be really annoyed at somebody doing a sample of 4. But, you know, I can't do anything about it. We're comfortable in how these questions are going to develop then. So there are 2 versions of this question. The one that we've spent a lot of time is, you know, you're told this, you're told this, you're told this, and then they say, find an 80, a 90, a 95, or a 90% confidence interval, you do this. They may finish with, how big do you need a sample be to be a particular margin of error? And that gets you through a big chunk of questions. They're all pretty much the same question. They just have different, pardon me, they just have different stories attached to it. So one of the stories, I'm just looking at one right now. You can't see it, but I'll read it to you. What price do farmers get for their watermelon crops in the 3rd week of July? So a random sample of 43 farming regions gave a mean of $6.88 per 100 pounds of watermelon. They don't get paid a lot. Must be the supermarkets then. I mean, £100 of watermelon's a lot of watermelon, right? And it's not one watermelon, right? Who knows how many it is, but that's a little bit weird. And assume that sigma is known to be 1.92, $1.92. And you've been asked in question A to do a 90% confidence interval. Okay. Typical, type the numbers in, got your answer. Part B is, he wants a margin of error of 0.29. How big should his sample size be? Isn't that this guy here? Right. You want a 90%. What magic number will you use for a 90% where my finger is? You won't use that. That's for 80%, right? Anybody got it handy? What's the Z of 0.9? 90%.
1.645.
Right, so can you imagine you just change the numbers to suit the question and you'll get 42, 50, 199, whatever it is. And then the next question. Oh, that is a good question. Okay. In this story, the values that they gave are in units of 100 pounds of watermelon. Evidently, that's a kind of going rate for watermelons. You tend to sell them and buy them in like 100 pound units. In the last question, this farmer brought 2,000 pounds, which is basically 20 units, right, of these things. And we're being asked how much cash he's going to get. Well, if you know the numbers, don't you just multiply each number by how many units? So if it's 20 units or 200 units or whatever, you do that. And that's the end of that question. So when you come to do it, you'll recognize it's a multiplication, I hope. So now we're going to look at, well, that's weird. It's over here. Right, let me stop sharing that one. I wonder if I put this here. I like my white screen to be in front of me. It's just easier for me to stare. Right, that's it. So, to recap, if I tell you X bar is 50, the N is 200, and that sigma is 43, and I ask you to find a 95% confidence interval, are you happy about how you would do that question? Am I saying lots of nods? So be happy about how you would approach that question, and you'd probably guarantee to do it the way I would suggest, right, on the calculator. A kind of addition to that question is, suppose they went and said, keep everything the same except, you know, what should N be, right, to get a margin of error of 15? Do you know how to calculate the size of a sample to create a particular margin of error, right? That's basically just plug and chug with that, you know, ZC sigma over E all brackets squared guy. Right. Okay, then I am calling that good. So what's going to happen next? Well, let's suppose that you take it one step back. I'm not going to tell you X bar. I'm going to tell you what the real numbers in the sample were. But apart from that, same question. So let's suppose that, actually we can do your class. Shouldn't take too long. Do you mind sharing your age? Right. Now, I'm lazy and I don't want to type in everybody. So I'm only going to take 8 people. So you know that you're self-selecting, which means that my sample is already biased, but can we pretend it's not? Just start checking out numbers. I'll start writing until I've got 80.
27.
29.
26.
22.
23.
31.
2 more to go. Oh, 64. I got mine in. Last one.
18.
18. Okay.
19.
Sorry. You missed the bus. It's left. I want a sample of 8. I mean, I could add your number. Okay, I'll add it. Right. Feels a bit cruel to leave you out. Now, we are going to have to create a confidence interval from this data, right? That's the only difference. The data isn't X bar equals, right? The data is this. What kind of confidence interval do you want us to find? 90, 95, 99, because there's the numbers I like.
95.
Wouldn't it be nice if this entire question could be done on your calculator? Be cool if we didn't really need to do too much in the way of setting it up and creating things. Well, that's exactly what I'm going to show you. And I'm going to use the calculator, the big calculator that I've got, because I think it might show up a little bit better. So you're looking at this guy here, right? So switch my calculator on, and here's the first change. I'm going to hit start, but I'm going to press number 1 edit. Because don't I have to tell the calculator the numbers to work with? Right? It doesn't know otherwise. So I'm just going to type your ages in, and hopefully I don't screw up too much. Now, we're going to take an estimate of the average age, and we have to think who this population is. I don't think you are a fair representation of Americans, all American adults, but I think you're a pretty good representation of Olympic College students. Would you agree? So we're going to use your sample to make a prediction on the average age of Olympic College students, right? Agreed? So step 1, put the data in, done. Now you hit start and you go over to tests, just like we always did. You go down to number 7, just as we always did. And now we do a changeover. You see, we were using this menu called stats. I'm going to move over to this menu called data. Now, you see it's changed a little bit. Oh, and I forgot to tell you something. In these questions, isn't sigma known? So can we pretend that I happen to know that sigma is 15? Nobody knows how the book knows sigma. We just trust them that they know it, right? So you're trusting me that I know sigma is 15, right? Because it's part of the story. Now, sigma then is 15, so I'm putting that in. And do you see it list L1? That means I'm going to get the data from L1, which is fine. I've never found a reason to make that any other number except 1, so just never touch it. And we wanted a 95. And I should be able to hit calculate. And our 95% confidence interval, and I'm going to be really, really rough on the rounding off here. I'm going to call that 18.9719. And I'm going to call the other guy 39. And the average is, I'll make that a little bit more accurate, 28.8. So what we've been able to do here is create a 95% confidence interval, right, for the population mean. And this is OC students, right, because that's our population. Somewhere between 19 and 39, roughly, right? And I'm 95% confidence that somewhere in that interval, the true average age of OC students is in that range somewhere. Now, a couple of things that people assume that are not true. They think that 28.8, if you had to guess one number, they think 28.8, the sample mean, is the best number to choose for what the real answer is going to be, right? The real answer is just one number, right? It's a population number, but it's one number. And it's not. Do you know 19, 20, 38.1, 33, 26, anything in that range is just as good a guess as any other number. So every single person in that range could have been the population mean. This number is no more or less likely than anyone else. And a lot of people kind of get a gut feeling that this guy is kind of a better guess than some of the others in the interval. They tend to think that the ones towards the outside, for instance, are less likely to be true than the ones that are kind of more in the middle. And that's not what a confidence interval tells you. It just says somewhere in that interval, and anybody in that interval is just as good as anybody else. and I'm 95% sure it's somewhere. 95% confident. So would you agree it's just one extra step? Put your data in AL1 and make sure that you use your interval accordingly. Cool. So this is probably the most realistic situation that you're ever going to be doing. Can you imagine you're doing a chemistry experiment and you do it, you do it multiple times, right? And you try and be as accurate as you can, and you collect a whole set of data. Perhaps it's this data here. If you create a confidence interval like this, can't you be saying to yourself, well, I'm 95% confident the percentage of the stuff in front of me being calcium is 19 to 39%, right? So you've got a mixture of all sorts of stuff, but how much of it is calcium? There's your range of values. Isn't that much better than just saying it's 28.8? How good a guess was that? Was that a really good scientific experiment, or was that a kind of dodgy one? And can you see you get an idea of variation? Imagine a totally different question. And I told you that a 95% confidence interval gave me that guy. And I have another guy, different fella, he did his experiment and he got the answer . Do you know which guy I feel I want to use as my predictor? Isn't this one giving me information that's really very tight and very precise? And isn't this one, it's all over the place? Well, if it was a chemistry experiment, aren't some people really good at being very nitpicky and precise about everything they do? And they tend to get data that is very good data. And aren't there some people that just that looks about 4 and they stick it in, and that looks about 2 and they stick that in? Well, can you imagine those kind of people are going to get data that's all over the place? So you can look at the same experiment with the same confidence interval, right? You did yours and John next door did his, and yours might be that and John's is that, and you're thinking, why are they so different? Well, maybe he wasn't doing a good job. Maybe he was lazy. Maybe he only done it 4 times. And you want to get an A, so you did it 40 times. Wouldn't that change the size of the interval as well? So we have a really very practical process now. I could collect data on anything you want, as long as somehow or other we know this guy, which is a little bit inaccurate. But if we could get by the hiccup of how this appears, right? I could collect data on anything, couldn't I, and get pretty good confidence intervals and make pretty sensible conclusions. I could, for instance, if I return back to this one here, couldn't we say that not only am I 95% confident that the real answer is somewhere between here and here, couldn't I say with a fair degree of confidence that the answer is bigger than 18? The real answer is bigger than 18. Why? Well, aren't all these numbers bigger than 18? On the other extreme, couldn't I be pretty comfortable or pretty confident that the real answer is probably less than 40? And the reason I can say that is that all the numbers are definitely less than 40, right? So you can sometimes get questions where, yeah, you get the interval, but they ask you things like, here's a few statements, which ones can you actually say? I couldn't say that this tells me with any degree of confidence that the mean is bigger than 25. Because isn't 25 in this interval? And isn't there a good chance that the mean is actually less than 25 and not more than it? So when you're looking at that question, if everybody in the interval, it's true, then you're pretty comfortable with your conclusion, right? But if you choose something that's in your interval, then you can't really say for sure that what that the average is bigger than 20? Because isn't it just as likely to be less than 20? It could be anywhere. We cool? So I think what I'm going to do is I'm going to create, hopefully you got your calculator, I'm going to create a little data set for you, and you are going to get a 99% confidence interval on it, right? So if you've got your calculator, that's great. Hopefully you have. Otherwise, I guess you're just going to be watching us do it. So here is your data set: 9.1, 5.7, 5.9, 6.2, 6.3, 6.7, and 8. 1, 2, 3, 4, 5, 6, 7. So here is a very small sample set, and I would like to get a 99% confidence interval, given that they tell me that sigma is 5. So using this data set, find a 95% confidence interval where the population standard deviation was 5. Last few things. Looks like some of you have got there. Okay, I've just typed in the data into L1. I'm now going to hit Start button, over to Tests, and choose 7. Right now, it's on the Stats one, so if I move it over to Data again, I can then move down, and sigma was 5 in this case, so I'll type in 5. Pretty much leave these two guys alone. I want a 99. I mean, when you think about it, isn't that really fast? And apart from, be careful when you type the numbers in, isn't that probably the only place you're going to screw up? I think most of the rest is pretty obvious what you do. So we are looking at a pretty mixed bag of numbers. It could be as low as, well, let's call it 2.0, because I don't want to write too many digits. And it could be as big as 11.7. So from this data set, we are a 95% confidence interval. So we're 95% confident that the population mean is somewhere between 2 and 11.7. It's a pretty horrible interval, right? There's a lot of room in that interval for the real answer to live, right? It could be as small as 2, could be 5 times bigger, right? It could be 11 in a bit. The main problem, sample size, sample size, sample size. When you collect real data it's not uncommon for the sample size to be over 1,000. That's what Gallup poll does. They do about 1,020 odds typically. And can you imagine that when it's that kind of thing, that calculators, although they do the job, can you imagine it's going to be done by computer? So basically, the computer just, you have, I think you still have people called data entry people. That job would drive me crazy, but basically they sit by a computer and type in the numbers that are on the pieces of paper so that the computer has them, right? And then the computer does it. So a data entry person would be the person who did this job, right? Typed all those numbers in. Oh God, that job would drive me crazy. I would be brain dead in a week if you gave me that job. But anyway, somebody else would do it, and I'm not criticising the job. I'm just saying it wouldn't suit me. And you get it, and it's done. The government data tends to be like way out there. You know, it's not unusual for government data to have 1 million people in it. Right, samples of 1 million. And in fact, won't the census data probably have hundreds of millions of people in it? Right. You don't do that in a TI-84, right? That's just not going to happen. But when the government takes that data, do you know, this is the kind of stuff they're going to do to it. Wouldn't you like to know, you know, if you only got some people from Washington, wouldn't you want to kind of use this to try and predict what everybody in Washington would be? Things like that. Now, before I forget this, let's suppose I want to know how big to make my sample, right? What n gives me a margin of error of 0.2. So I would need to figure out how many people, or whatever this came from, people, right, would I need to get this fella going. Right, now, the formula is the magic number for 99 times sigma divided by the margin of error squared. The 0.99 guy is 2.58. Okay, just notice something. Yes, this is 2.58. You may go online and look at other videos, and this will be 2.575. You know, that's just 2.58 rounded off, right? So just in case it happens, sigma is 5, and I want a 0.2, and I'm going to square the whole thing. So here we go. Put a bracket around it. 2.58 multiplied by 5 divided by 0.2, close the brackets and square it. Whoa. Uh-oh, made a mistake. Shouldn't you always round up? You would need a sample size of about 4,161 to get a margin of error of 0.2. So I can imagine what might happen. You're a company that wants to find something out about the people who buy your products. And you go to a company like Gallup, and they'll say, okay, well, we can find the average, whatever it is you're interested in, right? The average amount of money people will spend on washing up liquid, right? So you've got an idea of product placement, right? What's a good price for me to probably get the greatest number of people to buy my stuff, right? Whatever the decision is. So you go to them, and they'll say, okay, we can do that for you. What kind of margin of error do you want? Now, if they say, oh, I don't care, plus or minus 10, you know, you might only need to ask 100 people. But if they say, no, I want to know within a penny how much they're willing to spend, right? I want it really accurate. Can you imagine you could have to ask 10,000 people? Now, I know what Gallup poll's going to say. Oh, well, if you want, we have a kind of sliding scale, right? I know what they charge, right? If you want 10,000 people, it's going to cost you $1 million. If you want 1,000 people, we'll do it for $100,000, right? If you want a, 100 people, we don't do that. It's not worth our money. But if we were going to charge you $500 or something, right, that would get you. So can you see that sliding scale? Their sliding scale, I'm pretty sure, starts at 1,000, because that's like their going rate, right? But you can buy 2 for 20,000 if you wanted, and obviously it would cost a lot more money. This poor guy might have to change his expectations, because I do not want to do this 4,161 times, right? So he might say, oh, okay, I can't get away with 0.2, but could I at least get 2, right? A margin of error of 2. Well, yeah, you could. Let me redo this calculation. And if you wanted a margin of error of 2, you basically just do that, right? Oops. You see my calculation now with 2? This number here is 4,000 and change. What do you think this is going to be when I hit enter? Bigger than that or less? So I've went from that fella, and I'm willing to live with a different margin of error of 2, right? Do you think I'm going to need to see more people or less if I'm going to choose this thing? Less, agreed. And let's see how much less. Oh, 42 people. Can you see the difference in how many people you need? Okay, that's 10 times bigger than that, right? I agree. But do you notice that's not 10 times bigger than that? Isn't that 100 times bigger than that? So see if you want, there's a rule of thumb. See if you want to double your accuracy, right? You have to increase your sample size by a factor of 4. It's the square of the accuracy, essentially. So see if I don't like the accuracy of my margin of error and I want to make it 10 times better, right? 10 times smaller. I will have to increase my sample size by 100-fold. 10 squared is 100. That's a nice relationship. I think this is a good point for us to have a 10-minute break, right? Well, I hope everyone's here. We're going to get started shortly. So, Daniel, you were getting your caffeine intake, I think. So, I better do a second quit on this. Okay, let's get started then. What's 7.2? 7.2 is going to be deja vu. It's going to look like we're doing exactly the same thing. And for all intents and purposes, most of what we're going to do is exactly the same thing, but there are differences. The main difference here is that you no longer know the population standard deviation, right? Sigma is unknown. And if you think about that, isn't that much more realistic? There's no real reason that you should know what the sigma population standard deviation is. It's very rare to know it. Most of the time, you don't know an awful lot about the population at all. I guess that's why you're picking samples, right? You're trying to find things out about them. So when we look at a situation like that, you're going to be given different information. Well, let's rephrase that. Mostly the same, but one piece is different. So imagine I was interested in those hummingbirds and I've discovered a new species of them on some little island in the middle of nowhere. And these particular ones, the average is 2 grams. So they're even smaller than those other ones. And my sample was of 25 of them because they're darn difficult to catch. So that's the most I could get away with, right? And I don't want to hurt them. So I catch them and I weigh them and I release them and maybe put a little ring on them so I know I've already counted that one once. So if I accidentally catch it a second time, I don't count it, right? So I got 25 unique birds, right? And they end up having a mean of 2. And a standard deviation. Now, do you know that's not the population standard deviation? That is your sample standard deviation. And this sample deviation is 1.32. I would like, based on this information, to get an estimate of what the population mean of these hummingbirds. So if I could catch all of them on this island, right, but the little blighters are too fast for me, right? If I could catch them, what would be the average weight of these hummingbirds? Well, let's suppose I decide I want a 95% confidence interval. If you were going to do it by hand, which we're not, this is what it would look like. X bar plus or minus TC S of X over the square root of N. Now, if I write down beside it what it would look like in the previous today, would you agree it shares a lot of the same format? So let's look at the differences. Would it not be the population standard deviation? I don't know the population standard deviation. What do I know? Well, I know my sample standard deviation, right? So I put it there. Would you say that that would be a reasonable, the best number you could use, right? I don't know the population one, but at least I can find my sample one, right? And I could use that. Now, this funny little guy here called TC, he takes the same job as that. But this is a major difference. Isn't Z of 0.95 always 1.96, right? Doesn't matter if it's N is 200 or N is 22. Isn't that the same magic number in every question? In 7-1. This little fella here, TC, in particular T of 0.95, right? It's called a student T. That's his name. The student T value. He is not fixed. For every sample size, so if N is 25, this guy is a particular magic number. And it's even a little bit weirder than that. There's a fella called degrees of freedom, which basically you take 1 away from your sample size and you get 24. And you go and you look up a table and it has degrees of freedom and it says 24. And then over here somewhere, it's got the magic T value of 0.95. And this guy here might be 3.8. But if your sample size is 50, then can you imagine further along there's a 49 guy and the magic T value is now 3.2. Do you see that for every possible data size, this fella keeps changing his value? Now, if you were going to do it by hand, which we're not, you would have to go to the back of the book where there's a big table like this, and you would have to figure out how many degrees of freedom, then you would read down till you get the magic number that corresponds to it, and that fella would go in here. So let's just pretend, because I'm making this up, that that was the magic number, right, for this story. We would do X bar, which is 2, plus or minus 3.8 times 1.32 divided by the square root of 25. And this is called the margin of error. So that's 2 plus or minus, see what this fella looks like, 3.8 times 1.32 divided by the square root of 25 is 5. So you're going to get, whoa, that was unusual, 1.0032, which is pretty much plus or minus 1, isn't it? So 1 to 3. Now, if you look at this table, right, the table of the student T distribution. If you get really, really big numbers, like 500, this magic number here ends up being the same value as your Z. So eventually the magic T number, as the sample size gets bigger and bigger and bigger and bigger, it homes in and it ends up being the same. So when you get these tables, they don't, like, you don't have to go to page 82 because you've got 1,033 people in your sample, right? You don't need that. You can stop at a couple of hundred, because by the time you get a couple of hundred, the T number and the Z number are the same number, in which case you're good to go, right? So these tables do stop eventually at a couple of hundred typically. Now you can imagine that was kind of messy to do, right? Especially by the fact that every single time you do this, isn't the magic T number going to be quite an awkward thing to find if you had to do it by hand. So this is going to now be the real data. So I'm going to redo the question. X bar is 2, that's 25, and the standard deviation is 1.32, and we're going to do it on the calculator. So if I can find the calculator, here we go. So I'll put it on. Is it on? It is on. I'm going to hit start. I'm going to go to tests, and I am going to scroll down, because that Z interval, isn't that the guy we've been using all the time right now? But that's for Z scores. Our fella uses T scores, so he's called a T interval. So you go to choice 8. Right, it's a minor difference, but you do it, and I'm hitting enter. Now, do you see that looks very, very similar? Here's a couple of things you need to tell me. So let's see what it's asking me. I'm on stats, which is perfect, right? That's what these are, right? I'm on my stats. I'm going to go, the mean was 2. The standard deviation was 1.32. The number of people in my sample was 25. And I wanted, I forgot what I wanted. Did I want a 95%? Yeah, okay. So I want a 95% confidence interval. So I'll make that 0.95 and hit enter and go for it. And the answer, the real answer, is it's somewhere between 1.46 all the way up to 2.55. So we now have a pretty reliable process for calculating confidence intervals when you don't know sigma. Right? Purely done by the features in the calculator. So if I had this as my interval, would you agree that 95% confident that the real population average or mean is somewhere in this range? Right. Secondly, couldn't I say with a fair degree of certainty that these hummingbirds have an average weight of at least bigger than 1.4 and definitely less than 2.6, or at least I'm 95% confident that that's true. So don't I have a kind of ballpark figure for how big this particular hummingbird is, even although I only found 25 of them, and that island might have 25,000 of them, I can still use this and it's valid. Look good? So we're going to be given, there are two versions of this question. This is version 1, where they tell you the statistics to use. And we'll do that. So X bar is 102. Sample standard deviation is 15. I did a sample of 200, and I want a 90% confidence interval. I've only shown you one. Go for it. See if you can make it happen. Find the 90% confidence interval on this sample. And make sure you're on the stat side. Last few seconds. If you kind of know what you're doing, it shouldn't really take you that long, right? It's just a matter of plugging data in and letting the calculator do the hard stuff. So here goes. In this story, it was 102. And the sample standard deviation was 15. The sample size was a healthy 200. And I want a 90% confidence interval. And then I'm going to do a calculate. Hopefully you get the same as me. So I'm looking at a number about 100.25 on one side and 103.75 on the other side. Do you notice that the mean, it will always be halfway between these two, right? It's right in the middle, right? The X bar. Always right in the middle, right? That's where it belongs. I'd like to know the margin of error based on this interval. You remember how we did it in the last situation? Because we're going to do the same thing here. Couldn't you subtract these two and half it, which was one suggestion? Or couldn't you just take this away from the mean and that's the other suggestion? Agreed? So what have we got? We got 103.75, take away 102, 1.75. So we could basically say that. Wouldn't that be just another way of writing this interval? 102, give or take 1.75, right? Give or take the margin of error. That's a pretty good number. Would you agree 1.75 is not that big? Pretty good number. So whatever it is we were measuring here, I'm pretty comfortable about the kind of interval. I'm 90% confident that the real average for the population is in here. Are we good? Right, so if you think back to what we did in 7.1, wasn't this kind of thing we did first, right? Where they told you the X bar, they told you the sigma, right? They told you the stuff and you made it. And then wasn't the second phase where they didn't tell you this, they gave you the data. Right? So that's exactly what's going to happen this time. We're going to have, I'm going to pick a really small data sample and we're going to try and use it to build a confidence interval. And I don't know, what am I collecting data here? Okay. Are you willing to share how many countries you've been to in your life? Different countries. So America counts as one. Canada almost counts as one. Right? You know, Canada really just wanted to be America, but they couldn't really buck up enough courage, courage to ask. So they pretend that they don't want to be, but I'm sure they do. Okay, chuck them out. Give me some, how many countries have you been to? If you're a military brat, it's probably 10, but whatever. If you can't quite remember, do a guesstimate.
3.
Okay.
10.
Wow. Who said 10?
Olivia did.
Olivia, are you a military brat or you just like moving around?
No, I do archaeology, and so I find myself in Bulgaria and Ireland a lot.
You know those two countries are both in Europe but miles away and totally different?
You know, interestingly enough, the Bulgarians have a lot in common with them. They like to complain.
Well, I thought you were going to say they like to drink a lot and start fights, which
Well,
is
that as
definitely...
well.
Okay, that's fine. Next, we need at least 5 or 6, right? If you want to volunteer. It might be 1, none wrong with 1. Anybody want to volunteer some more?
23.
Daniel, you didn't say that, did you? You're in the military. I don't think you moved around a lot, so was it your parents' fault?
No, I lived in Italy for 3.5 years and traveled all over Europe and Asia.
Oh, Italy is one of my favourite places. I am jealous as heck. There's tons of places in Europe. I've been to Italy quite a few times. God, you make me jealous. I wish I could go back right now. I'd definitely do that. My favourite place in Italy is Venice. If you ever get to go to Italy when all this nonsense is finished and you get some money, go to Venice. It is just brilliant. Rome's good, but I didn't like the Vatican City, and I thought I would. And I think I'm a bit of a snob. The reason I didn't like the Vatican City is it was too touristy.
No, the
I
Vatican.
mean, I'm a
like, the
tourist,
Apostolic Palace
but I
is
don't want
beautiful.
any other tourists there. I don't know how I can explain that, but whatever. Right, give me two more and we'll get this over with.
3.
3. And one more.
4.
Okay. I can tell looking at this data that we are going to be all over the board with the average number of countries people have been to, right? Can you just tell, right? But that doesn't matter. You got to do this in statistics. Just because the data is ugly, you can't say, well, I'm just going to pretend I never asked him. And I'm going to ask somebody with a nice small number, right, or something, right? You're not allowed to do that, right? If you get horrible data, you just live with it and, move on. So this is going to be the data. Let's give it at least a fighting chance. So I'm going to find a 90% confidence interval, right? And the sample size is what, 5? Just ridiculously small, but whatever, right? Pretty much should be good to go. Well, almost. I'm going to hit start button. First thing I'm going to do is, I'm going to show you something really dangerous. So when I show you this, will you make sure that you memorize it correctly? If you want to get rid of a whole set of numbers, you could just hit delete and delete until they all go. Or you can move up to L1 and hit the clear button and enter. Now, why is that really dangerous? If you hit the delete button, L1 will disappear and you will not be a happy soldier, because then you have to figure out how you do everything else when that happens. So clear if you want to do that. Right, so here goes. You have to tell the calculator in these questions who the data is. Right, that didn't take long, right? Then you can hit start, and then you go over to test. Can you remember what number the interval that we're using this time, the T interval, is? Because it's not on the screen. Can you remember what number it was?
8.
8. So if you know what number it is, you can just type the number in to save you having to scroll. Right, it's 8. Now, this one is set up for statistics. So if I move over and I hit the data button, do you see it's now ready for the data? And it asks you very little, because all it needs to know is, where is it, L1? Always leave that as 1 and change that, or in this case don't, to 90%, and then go to calculate. And the answer comes out to be 0.43 to 16. Kind of what expected. You agree it's all over the place. Now, if I wanted to get a better confidence interval based on this question, wouldn't I have asked 50 people? And it kind of would have averaged out a little bit better, right? And a couple of really big numbers won't really matter when you share them amongst a big sample size. So that would have certainly helped. Have you noticed how similar the button pressing is to the section 7.1 stuff? You put the data in L1. All you do now is go to T interval, not Z interval, but isn't pretty much everything the same, right? Same process. And so we have got our guy. It even tells me that the mean number is about 8.6 countries, and the standard deviation of the sample is about, well, by sheer coincidence, is also about 8.6. Right. There's no reason in the world they should be the same, they just happen to be in this question. So if I was basing this class on how many countries has Olympic college students been to? The answer would simply be somewhere between no place, because they stayed at home, to 16 countries. That's a huge chunk of real estate, isn't it? But come on, 5 numbers. Now, if you were doing this in a practical question, you probably would want, I don't know, 50 numbers anyway, right? Something to get your teeth into. But that's going to take a lot of typing and a bit more care. But no matter what you do, you're going to have a lot of typing. Are we comfortable with the process on how to use what are called T distributions, right? The T interval, for estimating the mean of a population when you don't know sigma, which is much more realistic in my book, and it is. So let's stop this guy. And let's see if you wait a few moments, I can get in here and close that one off and get in here and click on that one. Okay, now, where have you gone? You've disappeared. Ah, there you are. Right. Question 2 is very like the question I've just done. Can you see it's just lots of numbers? So can you imagine what's 3, 6, and I think there's 9 numbers there. I'll double check. 1, 2, 3, 4, 5, 6, and right. So don't you just type them into L1? And you are going to, in this question, calculate the mean and standard deviation first. And then later on, you're going to get the 90% confidence interval. Can I tell you, it's better than that? Although you can't see it, right? See this guy here? Didn't you get for free the mean and standard deviation? So basically, couldn't you do A and B all at the same time? By simply just plugging your data in and using the T interval and then just writing down your 2 answers. Actually, I've got the answers here, which is fine, but you know, that would be the mean, that would be the standard deviation. And then you have the lower and the upper limit, which would be, you know, the interval. The first number is your lower limit, right? And the second number is your upper. And let me get the answers away here. Go away, key. Has this disappeared? I thought it would. I'll have to go back in and out again.
Oh, I meant just the answers disappeared.
Oh, good. I thought the whole
Sorry.
screen had gone. It's fine. It's back to square one. Can you see that you've really got a whole load of questions that are pretty much the same story? Here's some data. Find these 2 guys. Find the upper and lower limit with a 90% or a 95 or a 99 or, unfortunately, occasionally an 80, % confidence interval. I'm getting a lot of nods here. It might not be the most interesting thing to do. The typing isn't interesting. I think the results can be quite interesting when you just see them and say it. This one has bugged me. There are only 6 numbers, which is fine. We don't want you to have 600 numbers. You'd really go off statistics quite quickly, right? If you had to type in 600 numbers every question. So it's okay to be 6. And you'll get the upper and lower limit, and there's nothing wrong with that. This is what's bugging me. I think this is bad design. The question is, how much do wild mountain lions weigh? And adult wild mountain lions, that's 18 months or older, are captured and released in the San Andreas Mountains and blah, blah, blah. And here are the weights of them. And the thing that bugs me here is I think it's bad sample design. My gut feeling here is that there's 2 different groups of mountain lions. Aren't they the 100 and something mountain lions and the others? And my gut feeling, although I don't know a lot about mountain lions, but I know this is true in a lot of species, can't the males be bigger than the females? So wouldn't this be more realistic to actually have 2 samples, maybe with a few more animals? you know, maybe 6 or so male mountain lions and 6 or so female mountain lions. Because if you catch a mountain lion and it's a male or a female, don't you want to know, does that lion kind of fit in the kind of average weight for a mountain lion that's a female? Or does it fit in the, you know, if it's a male, does it fit in the average for a male? One of the things that they do when they are testing or checking for how well the wildlife is doing is that they weigh them. And you have to have a kind of normal value. This is what a typical mountain lion weighs, right? And then you go out there and you sometimes they do trapping, right? They stick a male inside and the thing goes in and the door shuts, and then they go in and they tranquilize it and they weigh it. And they actually don't need to weigh it. I think they pick up the crate and they weigh the crate, and they know how much the crate weighs and they subtract it, and that's how much the mountain lion weighs. Whatever, right? They get the weights of it. And let's just pretend that a normal, healthy male mountain lion is 120 pounds. If they go to wherever it is and they get 5 or 6 mountain lions and they get the same kind of numbers, isn't that probably a good sign the mountain lions are doing fine? But let's suppose that they get 5 or so of these mountain lions and they're coming in not at the 120 mark, but at the 105 kind of mark, right? Then isn't that probably a sign that the mountain lions are having food issues, right? They're going skinny, right? They're going hungry. And that could be, you know, bad weather, not enough, I don't know what mountain lions eat, right? But not enough of the creatures. It could also be a reflection, couldn't it be, of overpopulation? Too many mountain lions in one territory, not enough resources for them to live, whatever. But see, you've